We have 1 week left. Okay, so we have 1 week left, which is 2 classes. I have to use 1 class for the practice exam, so that leaves 3 lectures. 1 is used for the practice exam, so that leaves like 2 lectures left to present materials. So that's why we're kind of running low in terms of time left, and we still have quite a few topics to go over. Particularly, I want to go over at least the data structure and how to deal with C structures in assembly language programming. So those are the topics that I think are fairly important because just because of the nature of those questions or those topics. So we'll get started with topic 10. I know it looks like I skipped a few topics, but I actually did not. Because last time we talked about parameters, local variables, and return values. So topic 9 is really kind of we talked about that already. Your factorial program actually has to make use of those concepts. How many people have at least gotten started with your factorial program? What do you think of it? It's okay. All right. So it's a good entry point to the discussion of what we are going to talk about next, which basically are data structures. Eventually, what we want to be able to do is to look at any C program and be able to understand how to implement it in assembly language. Okay, that is the objective of this class. Is at the end of the semester, we want to be able to do that. Okay, and this part does not work. Okay. So let me fix that link first to make sure that works. There we go. So we talk about data structure here. And all right, so all of these concepts, are things that we should know already by now because they're all basically concepts that we know from C and C++. So we kind of go through this, one by one, and then I'll give you sample programs of, how to use, how to make use of these particular concepts. And oh, by the way, I'm going to give your test back to you. I'm not done grading it yet. But I have made photocopies already. I have to destaple every single one, run it through the scanner, and restaple every single one. So that took a little bit of time, even though this time my cat was not interfering. When I did this last year, my cat was interfering, and I was running a really big batch job, and I had to redo the whole thing from the beginning, because it jammed the scanner. This year, that didn't happen. All right, so we'll start with pointers. This is a topic where we should all know already because you guys have taken CISP 360 already, and in CISP 360 they definitely talk about pointers. So I just want to give you a very simple program, and then I'll present how it is done, and then we can move on from this topic. Okay. All right. So the way I'm going to do this is I will give you a sample program. Let me go to this folder here, and I'll just call this PDS.uppercase S. And in here, I will give you the assembly. I'll give you the C code of what I'm trying to do, and then I'll do it in assembly code just so that you can see how it is implemented. Okay. Just a quick reminder, no food or drink in the classroom. So if you have any drinks or food, just kind of not use it during class time, and you can, plain water is fine, okay? In the beginning of the class, I made the point that plain water is okay. All right, so we'll go ahead and just make one particular subroutine, and I'll just call this subroutine reset. And all it's going to do is to reset an integer to 0. So that's basically all it is intending to do. All right, so here's my C subroutine that I want to implement in assembly language. The question is, how am I going to do this? Well, it does have one parameter. So the previous discussion regarding parameters and also the frame pointer will still be useful in this case. So the first thing I need to do is to do a .global reset so that the linker is aware of the label reset. Are there any questions back there? Can I answer your questions? Any questions for me? Okay. All right. So the typical thing that I do is, yes, go ahead.
Font size.
Font size? Bigger?
Yeah.
It's under preferences, appearance. Let's try 18. Is that okay? All right. All right, so back to this particular program. So I'm going to use the same thing that I usually do, which is to define the offset from where EBP points to, and I'm going to use these labels to identify where those particular offsets are useful for. And it's not going to work because the projection screen itself is not aligned correctly, so I have to move the logic.
Tool.
The precision alignment tool, yes. Factory issued. So OEBP equals to 0 because when the frame pointer is set up inside the subroutine, it points to its own previous value. And that's why I define the label OEBP to be 0. For the most part, these are really for documentation purposes. The return address is right above the OEBP because the return address is pushed on the stack by the call instruction from the caller. So that's why this is usually at EBP +4. And then on top of that, we have our parameters. In this case, we have one single parameter called PTR, which is a pointer to an integer. So we have PTR here being return address +4. The reason it's return address +4 is because the return address itself is only 4 bytes long. So that's why this is where we'll find the parameter PTR itself. Okay. So once we have all of these defined, I can now start to write the subroutine itself, which starts with reset. The first thing we do with all these subroutines that make use of EBP as a frame pointer is the first thing we do is to push the value of EBP. The last thing that we do is to pop the value of EBP back into EBP itself. And then after this, I can take a snapshot of the stack pointer so that now EBP points to where the stack pointer is pointing at. And then right before we pop EBP, we can do exactly the opposite to restore the stack pointer to where it's supposed to be at before the pop L instruction. Are there any questions about these instructions? These are fairly standard instructions that we use for every single subroutine when we make use of the frame pointer EBP. Any questions about these?
Could you go over the last two codes for move L's between ESP and pop L? Does it do literally what I think it's doing? Or
Yeah, it does. There's no trick to it. The move L EBP to ESP will basically balance the stack pointer in one single shot. So if I have any local variables to use up additional stack space, this will basically reclaim all that space in one shot. I don't have to have individual pop instructions to restore. Okay, so the real question is, what am I going to do about PTR, this instruction here, or this line of C code here? Okay, so I'm going to give you one version that is incorrect, which is this one here. I'm going to move a 0 to PTR and then use the base addressing mode EBP And this is incorrect. Why is it incorrect? I'm certainly copying a 0 to some place, and I can tell you if the subroutine is set up correctly, this is not going to cause a segmentation fault, and yet it is not doing what it is supposed to, because it's copying a 0 to where?
Pointer itself.
To the pointer itself. Okay, so it's turning the pointer, which is a parameter, to 0. So this is not correct. This is the incorrect thing to do, because if I want to write what this is actually doing, it is saying this. Okay, which is not what the subroutine is supposed to do. The subroutine is not supposed to change the pointer itself to 0. It is supposed to turn what it is pointing to 0. So I have to have a way to do the dereferencing. And the correct solution to this, so I'm going to comment on this instruction because it is incorrect. So the correct way to do this is to move PTR EBP, which is a pointer, to a register. I'm just going to pick EAX because EAX does not need to be preserved. And then I can move a 0 to where EAX points to, because EAX now is the pointer, and I'm just going to reset where it points to 0. So this will get what what the original C subroutine is supposed to do. Are there any questions about this particular code? How do I check it? Okay, I can claim that this is going to work all day long, but how do I check something like this? GDB. I can use GDB. I can make a very simple main function and call this subroutine from C and see whether it works or not, right? So let's go ahead and do that. So I'm going to save this program first, and then I will use main.c to define a main subroutine to test whether this is working or not. I will have a PTR, reset int PTR like that as a prototype, just to make the C compiler happy. And then we have the main subroutine itself. Inside, I have a local variable I, and I'm just going to call reset to reset I to 0, and then I can check this. Now, what I can also do is to make sure that I starts with a non-zero value, so I can check, because if I start with a 0 value to begin with, I cannot see whether it is the effect of the reset subroutine or not. So I'm going to initialize I to, say, 1000 in decimal. So anything other than 0 is going to be okay. And then over here, I have return 0 as the end of the main subroutine. And that's it. That's all I'm going to use. I'm not going to spend the time to set up a makefile, so I'm going to cheat a little bit and just use GCC on both files. So I can use GCC-G-O. Main is the executable name, and then I can give it the source files. One is ptr.uppercase-s, the other one is main.c. And it will do the compiling, the assembling, and also the linking all in one single command. Okay, it's all done. So now I can say gdb main list, put a breakpoint on line 9 because I want to observe whether it is now 0 or not, and just run the program. Now, when you are trying to do something like that, with homework assignments, or you're doing your own experiment to see whether your understanding is correct or not, don't do it this way. Put a breakpoint in reset so that you can follow through the subroutine step by step, and then come back into the main function to see whether the effect of reset is what you expect it to be. Okay, I'm fairly sure this is going to work, and that's why I'm putting a breakpoint after the subroutine has returned. Run the program. No segmentation fault, which is good. And some of you talked to me about this one too. I have no idea why it's complaining. Could not load share library symbol linuxgate.so.1. I think it's just because the support library does not have the source code loaded. It doesn't seem to affect any type of debugging that I need to do, so it's okay. What I do want to do is to print the value of I, which is a local variable of main, and it is a 0 at this point. So the subroutine does what it's supposed to. Okay. Are there any questions about this particular program and how I implement dereferencing using assembly language? No questions? Go ahead.
Can you go over why that one line didn't work where you said it would just make pointer equal null?
Because it is copying the 0 to the parameter itself, not to where the parameter is pointing to. Okay, all right, so this is working. What about taking the address of a local variable? Okay, because can we do that in assembly? So I'm going to write another subroutine to do this. I'm just going to call this other subroutine, just call it useless, because it is useless. Okay, so useless as a subroutine looks like this. Okay, void useless does not take any parameters, and all it does is to declare a local variable, let's say int, and then it will call my reset subroutine with the address of I. So I would now be changed to 0 for sure, and then that's the end of it. And as you can see, it is completely useless because it allocates space for a local variable, it resets the value of the local variable to 0, and that's it. Okay? So it is completely useless except for the purpose of illustrating how do I take the address of a local variable I and pass it along to another subroutine. Any questions about what this C code is supposed to do? Questions? Everybody know about the ampersand operator, address of, and everybody knows that local variables are on the stack unless it is declared static. Okay? Did your C class talk about static local variables or not? Okay, they do. Okay. It's very seldom that we want to do any type of static local variable because any subroutine with a static local variable is not reentrant, which means it cannot be thread safe for one thing, and two, it doesn't work in recursion either. So there are many reasons why we do not want to use static local variables. Okay, so now we want to go through the stack frame first. Okay, ODBP is 0 because the frame pointer is set up to point to its own old value. The return address is one word on top of that, which is OEBP plus 4 because EBP only takes up 4 bytes on the stack. In this case, I don't have any parameters, so this accounts for everything that is related to me as far as this call frame is concerned. I do not have any parameters. But on the other side, I do have a local variable I, so I better allocate space for that. I is on the negative side of EBP, so I is old EBP minus the size of I itself. Since I is just an integer, I'm going to subtract 4 as the size of the integer. And that completes the definition of the call frame. So it's time to declare that useless is going to be exported to the linker. And here is the starting point of the subroutine. As with all the other subroutines, I use the same procedure here. I save EBP, and then I copy ESP to EBP, so that EBP becomes the frame pointer of this particular invocation of useless. At the end, I do exactly the opposite. I restore the stack pointer, and then I pop L EBP, so that as far as my caller is concerned, EBP, the value of EBP, has never changed, because I save it first, and then I restore it before I return. So as far as my caller is concerned, EBP has not changed. And then after that, I can do the return. So inside here, I also need to allocate a space for my local variable. So if you want to do it in a fancy way, you can always define last variable to be the last local variable. So this way, inside the subroutine here, I can just say add long $last var last local variable to the stack pointer. If you track down the definition of the labels, last var is really just -4. Because ODBP is 0, I is 0 minus 4, which is -4, and then last var is the same as I, which means it is also just -4. Adding -4 to ESP is moving the stack pointer down by 4 bytes to reserve 4 bytes for my local variable I. Are we still doing okay so far with all of these instructions? Okay. So this completes the setup of the call frame. Yes?
Maybe the last function, we have like a PTR is equal to return address plus 4. So now, and then right now we're doing I is equal to ODB plus 4.
Because I'm reserving 4 bytes for my local variable I.
And remember we did last time for the PTR is equal to return address plus 4, what was that doing? The
That's my parameter. Parameters are on the positive side, and local variables are on the negative side. Because only a subroutine can reserve for its own local variable, but the parameters are set up by the caller, so it's on the positive side of EBP. Okay, so now the question is, now that I have set up my local variable, it is time to pass the address of my local variable on the stack. Okay, so I'm going to start with an incorrect instruction first, so that we understand it is not this instruction, it is something else. I know I have to push my parameter on the stack, and I know how to access my local variable like I, but this would be wrong. Because if I use this instruction followed by a call to reset, what I'm really doing is I am pushing I itself on the stack and not the address of I on the stack. Is that okay? Because I is a displacement from EBP points to local variable I. So this is really just pushing my local variable I on the stack, but not its address. Reset requires that I pass the address of I, so this is not going to do the trick. Okay? This is incorrect because we are passing I on the stack, not the address of I. So we cannot use that instruction. I better comment it out because it is incorrect. So in order to push the address of I on the stack, there are a few ways to do it. Okay, so I'm going to present a few ways to do this. The first way to do this, I'm thinking about how to structure this so I can show you multiple ways of doing the same thing. The first way to do it is to do the calculation in another register. So to do the calculation in another register, we basically can move ESP into EAX, for instance, and then we add the displacement of my local variable to EAX, and then we can push EAX on the stack. That will accomplish what we need to do because we are computing the address of local variable I in EAX, and then we push that on the stack. So that will get the trick done. I mean, that's one way to do it. Are there any questions about these three instructions? Why combined they would push the address of I on the stack? Yep.
I don't understand how do we know what I is, because we not pass I from a caller.
In general, your call frame looks like this. At the highest address will be the parameters, because the parameters need to be pushed by the caller before the call instruction, and that's why if they're pushed first, they have a higher address on the stack.
But we didn't push parameters.
We don't have any parameters, but I'm just going to show you, what a call frame looks like
I
in
know
general.
how call frames look like, but I don't know how do we know I, where is I? We didn't push it.
Ah, but we did do the add last var to ESP. That reserved the space.
It's reserved space, but what value? I understand that we reserve the space, but space for what? How are we going to push?
I think it's kind of the same.
Well, let's take a look at this picture. Let's look at this picture first.
You can use push and you can use just move.
Yeah, push is different from what I do because push allows you to specify the initial value. Because in addition to moving the stack pointer lower, it is also copying the content. Like if you push $0 on the stack, you're initializing those 4 bytes to be zeros. In this case, I'm just moving the stack pointer lower by 4 bytes and not really care what those 4 bytes are. I'm just saying that, okay, here's the stack pointer at one point, and now here it is. But I don't really care what is here, and that's why it is uninitialized. So local variable I, just like in the C equivalent program, is not initialized. Okay, but I do want to kind of finish this picture. Okay, so we have parameters here. We have the return address here because it is done by the call instruction, and then we have the push EBP instruction. So that's why old EBP is over here, and then we copy the stack pointer at this point, and that's why EBP points to its own old value. And then after that, we reserve space for my local variables. And as a result, after everything is all set up, ESP will basically point to here, and then we can do additional pushes if we need to, but it's not going to change the offset of everything coming from the perspective of EBP. So in this case, we only have one single variable as my local variable. So this portion is only 4 bytes long. Okay. All right. So this will get the trick done, but there are other ways to do it too. I'm going to use this trick here just so that I can show you the code, but it's not going to assemble. Because I can use pound if and pound end if to block off a block of code, and so it won't compile. It won't be assembled. Another way to do this is a little bit trickier. I can push EBP on the stack first, and then I can add the constant I to wherever the stack point is pointing at, and that will do the same trick as the previous 4 instructions. Let me turn on the line numbers so I can refer to, to the lines here. So lines 27 and 28 will accomplish pretty much the same thing as lines 23 to 24, 22 to 24. So it will do the push and do the calculations, basically combined using only 2 instructions. I will leave it up to you guys to study this and make sure that they do exactly the same thing. Okay? So I'm going to choose the second way of doing things just because it looks cool. Okay? We're pushing something on the stack, and then we modify what we just pushed on the stack. Because by definition, the stack pointer points to the last thing that we push on the stack. And we just push EBP on the stack as the last item. So it would accomplish the same thing as the other 4 instructions. At this point, since the parameter is pushed on the stack, I can now call the subroutine called reset. When reset comes back, I need to clear the 4 bytes on the stack, because the parameter is of no use to me as a caller. So I'm going to add 4 to the stack pointer to reclaim the space of the parameter. Now, technically speaking, I don't have to do that because the last instruction is going to reclaim the space on the stack anyway. But as a good programming practice, as a habit, whenever you come back from a subroutine and you have parameters pushed on the stack, you should reclaim the space used up by the parameters. Are there any questions about this part here? No questions? Okay. So with this one, it is a little bit harder to verify that it works. I can implement reset in C and actually call reset in assembly from this code so that we can see what is being passed to reset to make sure that it looks right to us. But other than that, there's really not much that I can do. Let's go ahead and do it that way. So I'm going to keep this program like this one. And then what I'll do is I'll go back in main here. Instead of making reset just a prototype, I'm going to implement reset here. So reset is implemented as this, as what we intended to be, like so. And then we have the other subroutine called useless. And we'll declare useless as a prototype so that the C compiler does not complain about it. And in here, inside main, we'll change main so that it will just call useless. So we'll call useless for so this time when I test this program, I'm going to put a breakpoint in reset, and then I will make use of a particular feature in C and C++ to look at the call frame of everything before that. How did we get to this certain point? Okay. All right. So let's go ahead and do this part here. GCC -G. -G is required because we want to include all the debug information. And then -O to specify the output file, which is the executable. And then we can give it all the source file. In this case, is main and useless. Okay, it assembled, linked the first time. So now we can go into this subroutine. I put a breakpoint on line 5, which is inside the reset subroutine. Run the program. Now I'm inside the reset subroutine. So the first thing I want to do is to say, well, does PTR look like it is a valid address? Does it look like it is pointing to somewhere on the stack? What do you think? What can I compare PTR to see whether it seems like something that should be on the stack? The stack pointer itself, exactly. So I can say, print ESP and see whether the stack pointer is, well, the stack pointer is BFFFF something something, and then the pointer is BFFF something something. So it looks like the pointer is pointing at the right place, okay? Let's go take a look at another feature of GDB that can be helpful. So we type help in GDB. It shows that categories of instructions or commands that we can use. So we'll say help stack. Sorry? So we'll say help stack, and it shows us the backtrace. Okay, so backtrace is what we want. We want to print backtrace of all stack frames. In other words, I'm not only interested in the stack frame of reset, which is where I am at this point. I want to know how I got here. So in other words, in this case, I want to see that main calls useless, useless calls reset, and that's how we got here. And on top of that, I also want to be able to see what is the value of I in useless, which is the caller of reset. Okay, so you can do all that stuff here. It's almost magical. So we say BT, and it shows us the call stack. So it clearly sees, we can clearly see that main calls useless, which is in assembly, and then useless calls reset, which is in C at this point. I think there is a way to show the value of a variable in another call frame. So we want to take a look at select frame. So help select frame. Select a call frame without printing anything. An argument specifies the frame to select. It can be a frame, stack frame number, or the address of the frame. Okay, so the frame number refers to 0, 1, or 2. So I can say select frame 1, so I'll be in useless. Useless is the one that owns the local variable I. I can't really see variable I because it is written in assembly, so it cannot see that. Because if I say print I, it doesn't know how to get to I. So I can't really show you that. Oops, I don't want to quit just yet. Let's see whether this address makes any sense compared to all of the other addresses. One thing we can do is to put a breakpoint. Okay, put a breakpoint inside the reset subroutine. So I'm going to list useless uppercase S starting on line 1. And we are now in the call instruction right here. So when the call instruction comes back, we want to put a breakpoint on line 32. So we want to put a breakpoint on line 32 and just continue the execution of the program. Now we are back on line 32 of the assembly program, which owns the local variable I. Okay, how do I find local variable I? How do I start with locating variable I in this case?
Examine the stack.
Examine the stack, but the stack is pointing to, well, I guess, the stack pointer is not pointing to I right now because I have not reclaimed the space of the parameter. So what I should see here is the address of I followed by the content of I itself on the stack. Is that making any sense? Because I'm stopping on line 32, which is about to reclaim the space that is currently used up by the parameter to the subroutine reset. And on top of that, okay, so this is what the stack looks like right now. The address of I is here because I just called reset. So the stack pointer is pointing here. So if I do a dump or an examine, the first thing I should see is the address of I, and then I will see the content of I itself. Is that making any sense? Let's see whether that's related is the case or not. The X command is what we need. We're going to display 2 items. Each item is going to be a word, which is a 32-bit quantity. I want to display each one as a hexadecimal representation, starting at where EBSP is pointing to. Does it make any sense?
Yes.
Okay. The first part is the address of I. So the address of I is BFFF864. Well, this location itself is BFFFA60. That makes this location BFFFA64. So the address of I is correct. What about the content of I? It is all 0. Is it supposed to be 0 at this point? We just came back from reset, so it is supposed to be 0. So even though this is written in assembly, I can still double check and verify that the program basically worked the way it is supposed to. Are there any questions about this part or how to make use of the ampersand operator in C and C++? No question? Okay. All right. So at this point, I want to go back to the website here, just to kind of point out, where we are, what we are talking about in the concept, and how to do the referencing. And the next topic is, are arrays. So how do we deal with arrays in assembly language? Okay.
Allow a lot more on the stack.
Well, arrays are very evil in C and C++ because that's the one thing that you can use to corrupt the stack. It is very, very evil. Okay, so we want to see, how arrays are actually used, and then we will take a look at why it is really a bad thing. Okay, so the concept, I don't think I have to spend too much time on the concept itself. The indexes, have to start with 0. And this is why the indexes start with 0. Has anyone ever thought about, in your regular C, C++ programming class, why in array indexing is we start counting from 0? Has anyone thought about that? Yep.
I know the answer, kind of. It's like because that's where the stack pointer starts at location 0, kind of like it
Because
starts at location 0.
Because it's at an offset of 0 from the beginning of the array.
Right.
Yep. That's why it is starting with 0.
We're going to use user-defined indices.
Types.
And
user-defined indexes?
Yeah.
It's not supported in C or C++.
That's what we're. Oh, they don't support it at all?
I do not believe in C you can arbitrarily set the start index of an array.
We're doing it in code blocks in Fox's class, so I don't know.
That must be a newer standard then.
It could be. But we're defining all of our own.
If I remember right, I think he's using operator.
No, we like simulate. Just
Oh, okay,
simulate.
so it's not native to C or C++. You are simulating it using your own template class, basically.
we're doing our own.
And you're overloading the square bracket, the indexing operator. Okay.
Yeah.
That's cheating, using operator overload. So it looks like actual indexing, but it's not. It's just calling your subroutine or your own method to do
Yeah,
something.
From code, looks like it's not.
Yeah, you can also overload the address of operator. There are many operators you can overload. I'm not sure. Some of those you cannot overload, but most you can overload. All right. So the concept is easy. The allocation is also easy. Okay. So what we'll do is I'm just going to go through a few example programs just to illustrate what we do when we deal with arrays. So we'll call this array1.s so that I can illustrate a very basic way of using arrays in assembly. So this is also useless, but I'll call this array A as a subroutine. And what we want to do is simply to do this in assembly. I want to allocate an array. Let's call this, A is an array, and I want this to be an array of, let's say, 5 integers. Like so. And that's it. Okay. How do we implement a subroutine like this? Now, if you turn on, optimization, the C compiler won't even generate any actual code because it figures that, hey, you're declaring a local array A, but you're not using it, so why bother? Yep, go ahead.
Array is just a pointer, so you just allocate 5 bytes.
You have to allocate the space of 5 integers in this case. Okay, so we'll do this step by step. Okay, so we say .global array1, and array1 is the name of the subroutine, so we have to start with that label. And just like with all the other programs, I start with OEBP is 0, return address is OEBP plus 4, and then this time we have a local variable which is an array A. So A is on the other side of OEBP, and this time I have to subtract the size of the array itself from OEBP. In this case, each item is 4 bytes long, and I have 5 of those. So this is how I reserve 20 bytes on the stack for my local variable A, which is an array of 5 integers. Okay. And that's about it. I mean, there's really not much to say, except we have the usual entry point code to set up the frame pointer, and then we have the instruction to allocate the space for my local variable. So I have to add the displacement to my local variable A to the stack pointer, so I reserve that space on the stack. And then I have nothing else to do in between. To exit, I clean it up by just restoring the stack pointer from the frame pointer so it points to its own old value again. Do the pop L to actually restore the old value of EBP, and then do a return. That's it. So this means the allocation of an array in assembly is really not much different from allocating the space of individual variable. You just have to calculate the size of the array, and that's it. Are there any questions about this code at this point?
So then if you wanted, say, your pointer to point to the start of that array, then you could do that by pointing it to the array, basically, like
right,
to the
because
starting to the starting address.
Yep. This is one of the things about C that makes it very confusing, because every pointer is an array.
Right.
You can apply the index operator to any pointer, but you can also declare an actual array like this. So this is a real array where you know the address of the array itself, but when you use a pointer, you just know the beginning of the array, but you don't know how large the array is. Okay, so that seems way too easy. Let's go do something that is a little bit more fun. So we want to say, okay, let's change this instruction here. So let's pass a particular parameter I here, and in here I just say a bracket I gets 0. How do we do that? Now I know this subroutine is completely and utterly useless because I am just passing a parameter to control which element in a local array I'm initializing, and without using it later on for anything else. Okay, but it is still useful for the illustration purposes. How do we do this instruction here? First of all, I need to declare my parameter I now. Parameter I is 4 bytes after the return address, so I need to add this part here. That's the easy part. Okay. So I'm gonna put this code here, so this way I know what I'm trying to implement. How do we do this? There's a long way, and then there's a short way. The long way is to do all the calculations using the multiply instruction, so it's general purpose and all that stuff. The short way is to make use of a particular addressing mode that we have talked about, that we have probably forgotten by now. Yep, exactly. It is the full form of the complex addressing mode, the based scaled indexed addressing mode. Okay, and that becomes kind of helpful in this situation. All right, so let's take a look at how we can actually get that to work. First of all, I need I to be in a register, because in the general form, which is displacement, base register, index register, and scale, the I and the B, they have to be registers. So in this case, variable I, is taking the place of I because it is the index. So that's why I need to move it into a register first. Well, that's not too hard. I just need to move I EBP, which is the parameter itself, into a particular register. I can put it into register EAX. Okay. So now from here on, register EAX is the index to index into the array. I need to change one of the elements to 0 in this case. So the I need only one more instruction to get this all done. Okay, I can use A as my displacement on the outside, so A is the D in that general form. Who is going to be my base register? EBP. Okay, so combining EBP and A, I can get to the beginning point of the entire array. But then I can use EAX as my index register. What about my scale? 4, exactly. So that becomes the operand, but this is my destination because I'm copying a 0 into that location. So in this case, I can do it in 2 instructions only because the size of each element in the array is 4. And it's very handy because I have this particular addressing mode that can deal with it. Are there any questions about this? No question? All right. Let's do this in a harder way. Doing the same thing, but do it in a harder way. The attack way, exactly. If there's a harder way to do it, let's do it that way. Okay, so the harder way to do this is to call reset. I'm hoping you guys still remember reset, which takes a pointer to an integer. So what I want to do is to pass the address of element I of array A to reset so that I can use the subroutine reset to change that particular element to 0. Okay, so I'm going to write a C code first so you know exactly what I mean by that. Okay, so I'm resetting, this is the address of A bracket I. In C, it is really easy to specify. I'm just taking the address of one element in the array. Is that okay? So the question is, how do we do this? Someone is going to say, oh, that's easy schneezy. I just need to copy and paste that really complex addressing mode, push it on the stack, and then call reset. Okay? So let's see what this will actually do. So someone's going to say, yeah, we can do this. Call reset, and then reclaim that space by adding 4 to the stack pointer, and we're all done. Unfortunately, this is not going to push the right thing on the stack. What is this going to push on the stack? It is going to push the value of the element on the stack, not the address of the element on the stack.
So
Shucks.
Put it in the register and push in direct register.
That won't work either.
Why?
You mean something like this?
Yes.
That won't work because EBX is still the content of that element.
No, indirect.
Indirect.
Indirect?
In the parentheses. EBX.
But indirect is dereferencing. It is not taking the address off. It is you're moving in the opposite direction. There's really no easy way to do this. However, taking this completely out of context of what we are talking about, haven't we seen something like this in the previous exam? Because what we are doing is I'm trying to calculate the address of a complex addressing mode and try to put it into a register. We have seen something like this already in exam 2. In other words, I am trying to implement, well, okay, not exactly the same, but it is very similar to what we are trying to do here. Okay, so what we need to do is to calculate the effective address of this component. What do we do to compute the effective address of something like this? D plus B plus I times S, right? So we need to do each one of these operations using assembly instructions to accomplish what we are trying to do here. Then we'll end up with the effective address of that operand, and then we just need to push it on the stack. Okay? We have seen something like this. So the instruction to do this, or one set of instructions to do this, is as follows. Okay? We have EAX already being the index register. Assuming that I can destroy the register or the content of register EAX, I can just do something like this. I can say add long EAX to EAX, which doubles the value of the index. and then I can quadruple by doing the same thing again. So now EAX is 4 times I as my parameter. Is that okay? Okay, let me just kind of comment out the instruction that I do not want. Is that okay? So we have this instruction first to copy parameter I into EAX. This instruction is going to double it. This instruction will end up quadrupling the value of I and store that into register I at the same time. Effectively, I am done with this part already. Okay, I times S is done. So what is left to do is just to add the base register. In this case, it is EBP, and also the displacement, which is I in this case, to register EAX. Okay. Not I, A, excuse me. It is label A, not label I. Okay. So we can add the base register first, which is EBP. We add it to EAX. And then we can add the other component, which is A, to EAX. Then we all set push L EAX, because EAX is the effective address of that element of array of array A. We push it on the stack. We call reset. Reset will get its job done. We come back. We reclaim that 4 bytes on the stack, and we are done. So this is the long way of resetting one element, but I do want to show you how to take the address of an element in an array. Okay. Any questions up to this point? Have I introduced any new instructions in today's class? Push, pop, return, call, add, move. Very basic instructions. Have I introduced any new addressing modes? Register, immediate, base, scaled, indexed, based, that's it. So it is the combination of these instructions and addressing modes that allows us to do all these things that we are doing. Any questions about the use of arrays? No questions? And I think we are ready to move on to structures. So the big question is, how do we do structures in C? I mean, in assembly. We know how to do it in C and C++, but how do we do it in assembly? Okay, so this takes a little bit of a detour.
Yes, there's 2 ways, the easy way and the tack.
Which is also usually known as the right way. Sometimes. Okay. Well, it's the right way because I'm just going to do whatever the compiler is going to do. Okay, so I shouldn't say it is the right way. It's the compiler way. It's the GCC way. Okay, so we'll go ahead and write a very simple program that declares, that defines a structure, and then we'll basically say, okay, what are we going to do with this? So we'll go, we'll define struct1.h as a header file, because it is conventional to put structure definitions in a header file so it can be used by multiple files. So we'll say if not defined struct1_h. The first thing we do is to define it, struct1_h, and define here, and if. Okay. I'm going to explain why we have this little construct here. So we have structure, and I just call the structure struct1. And using the C++ convention, I'm going to use uppercase, for the name of a structure, because a structure is kind of like a class, except everything is public by default. So inside, I'll give it various components. I'll give it one component, which is an integer. I'll give it another char array here. It has like some really odd number of characters, and then we'll give it another pointer. Let's say char pointer PTR here. Okay. Don't ask me why we have these members inside this struct. It is just for example purposes. Okay. So we have a structure defined here. So let me go back and explain why we have the pound and def, pound if not defined, and then we have the definition, and then the pound and if here. This is needed so that I can write some code like this. Okay. So let me go back and write another program that refers to this .h file. So we'll say test struct1, .c. And in here, I'm going to include struct1.h, which includes the oops, not using this square, I mean the angle bracket, because angle brackets refer to system include files. I have to use double quote to refer to my local include files. I'm going to do it like this. Would that be a problem?
No.
If I did not have the pound if not defined, it would have been a problem.
I think it would be.
Say again?
You have like a mistake in the case.
Well, in this case, it's not going to be a problem because the pound and def is going to fail the second time, so it will basically branch around the entire block. Okay, let me just explain what I mean by that. Oops, save it first. Struct1.h. Okay, so if you look at, let me turn on the line numbers. All right, line 1 says if struct1_h is not defined, do the following until the matching and until we get to the matching and if, which is on line 11. But we are not going to do anything if struct1_h all uppercase is already defined. So that's how we can basically do the trick that I did earlier. I can do pound include of exactly the same file, and it's not going to cause a problem. Because the second time when I do the pound include, it's going to skip around the entire thing as if there's no struct definition in this file at all. Okay? Are there any questions about this trick?
Do you have two uppercase H's?
Say again?
Do you have two uppercase H's?
Two uppercase. Oh, okay. Yep, you're right. So it will not work the way it is because I forgot about that H.
So
Hmm?
I was pointing to this.
Oh, okay. Thank you. But this is a trick that is used by a lot of header files. But who's going to be so stupid to have two pound includes like that? Well, other than myself, probably no one. Okay. However, you will end up with pound includes that eventually will include the same file. So indirectly, you can have something like this by saying pound includes standard io.h, pound includes standard lib.h. They can end up doing a nested pound include of the same header file. So you still end up with the same problem, and you still need the same solution to solve that problem. Okay, so I'm just giving you, some additional stuff that you might not have talked about in your C and C++ class that is actually useful. Okay, when you write programs and define header files, this is one way to make sure that double including the same file is not going to cause a problem. Okay. All right. So in this file, I'm going to do something, not exactly very exciting. So I'm going to have my main program here, and I'll have pound include standard io.h, which is kind of the same thing as iostream, except this is doing it in the C way instead of the C++ way. And in here, I'm going to define a local variable of that particular type. So I'm going to say struct, uppercase struct 1, and we'll just call that var for variable. And one thing that I want to do is to have a whole bunch of printf statements. I'm going to say printf. And of course, I cannot remember the names of the members anymore, so I'm going to refer to it IAMPTR. IAPTR. So we'll say that the offset to I is, and then we use %d here. How do I compute the offset of member I from the beginning of the entire structure? Okay, so I'll give you, an option, and you guys tell me whether it will work or not. So one way to do it is I can take the address of var.i, which is the address of member I, and then I can say, oh, let's subtract the address of the entire variable from it. So this should give me the address of the offset to member I of this entire structure. Is this going to work? Nope, it's not going to work. It's not going to work big time because it won't even compile. What is the address of var.i? What is the type of member I? It's an integer, right? So the address of var.I is a pointer to an integer. What is the address of var? It's an address of a structure. Well, the two pointers or the two addresses do not have the same type, so the subtraction is not defined. The compiler will come back and complain and say it cannot do this.
Cast them to the void.
Hmm?
Cast them to the void.
Cast them to void. Okay, if you cast them to void, I don't think that will work either, because if you subtract an address from another address, they need to have a size in order for the subtraction to be meaningful. So I don't think this will work, but let's go ahead and give it a try. Okay? Because my knowledge of C and C++ may be a little bit out of date. So we'll just do a -C just to test it, so I don't need to really do any linking. And it worked. Okay. I take it back. The question is it going to be the correct number? So in this case, you should print 0 because member I is the first member of the structure. So we'll do a gcc-o test struct1, test struct1.c, and just run it. And it is 0. That's good. Okay. Now let's go to the other members of the structure. So I'm going to do a copy and paste here. The second member is A, I think. The last one is PTR. Okay. I should have defined a macro to do this, but that's going to take up a little bit more time. So this way, I'm going to print the offset from the beginning of the structure to each individual member. Is that making any sense? So let's see whether that works or not. In number of bytes, by the way. So we'll do another GCC, run the program again, and that looks right to me. Okay, because member I is at the beginning of the entire structure. As a result, it is at an offset of 0 from the beginning of the structure. Member A, which is the array of characters, is the next item, and as a result, it is 4 bytes away from the beginning of the entire structure. The last member, which is PTR, is the last one. Even though I picked 23 characters as the size of the array, the compiler can choose whether to pack the members inside the structure or not. By default, it does not do any packing, which means it wants everything to be a multiple of 4, and that's why PTR is at an offset of 28 bytes from the beginning of the structure. Are we? Yep.
You said 23 was the number. What are 24? 5.8. Like 24 plus that 4 or 8? Or
Well, A is already at an offset of 4. It has a size of 23.
20 plus 4 plus 7.
27, and we want to round it up to the next multiple of 4, and that's why we have 24. Questions back there?
Does it allocate 24 bytes or?
It actually allocates 24 bytes, even though I only asked for 23. That's because it wants to pad it so that all the members end with or start with a multiple of 4 from the beginning. You can pass certain pragmas to the C compiler to make it pack so that they don't leave any space, but by default, it does leave some space. Okay, great. So now I want to write an assembly subroutine so it can take a pointer to a structure and initialize a particular member of the structure to something. Okay, that sounds pretty, well, it's complicated in a way, but it is not complicated in a way. Okay. All right, so I'm going to do this in C first, and then we'll do it in assembly. So what I want to do is to define a particularly useless subroutine. So we'll just call this, more useless. But this one is kind of strange because it takes a pointer to a structure. And we'll just call this PTR. And I'm not going to do anything too fancy. I'm just going to say the PTR, the pointer member of the structure pointed to by parameter PTR, is going to be zeroed. Okay, I just wanted to point it. I just want to make it a null pointer. That's all I want to do. Does everybody understand what the C code is supposed to do? Okay, how do we do this in assembly? I'm going to split the screen so we can see how we do this in assembly. So let's go ahead and split the screen into 2 halves, and then in the second half, I'm going to use the other file called more useless.uppercase S, and then scroll this one back to this point here, okay? Because I'm trying to implement more useless, okay? Dot global more useless, and then we have the usual stuff defining the labels first. So we start with old EBP is 0, return address is old EBP plus 4, and then we have PTR is return address plus 4. Okay. We don't have any local variables in this case, so I don't have to do anything about local variables. So now I define the entry point of the subroutine more useless, and then we do the usual stuff, push EBP, move ESP to EBP, and then we do the undo part here, basically just reversing the operations, moving EBP to ESP, pop EBP, and then do a return. Okay, so that part is not really difficult. What is difficult now is how do we get, how do we change the PTR member of the structure pointed to by parameter PTR to 0? What do you think? Okay, so the program that I have at this point is kind of useful because it printed out the offset to the last member PTR. And if I remember correctly, it was 28. Okay, so that's useful. So what I'm going to do right now is to say the offset of struct1 to its member PTR is at an offset of 28. I'm just using this particular label to say, okay, the offset of member PTR of struct1 as a structure is 28 bytes. Does everybody understand the meaning of this label? Okay, so later on, I don't have to refer to 28 all the time. I just refer to a label to refer to the offset of this member from the beginning of a struct1 construct. Okay, so knowing this, what do we do at this point? Well, let's start with something like this. Okay, I think this might be useful. I'm just going to copy the parameter PTR to a particular register, let's say EAX. Okay, what exactly is EAX? I'll give you 2 options. Is EAX a structure of struct1, or is it a pointer to a struct1? It's a pointer to a structure. Okay, very good. And struct1 underscore PTR is a label that defines the offset of the member PTR in the struct1. So don't you think EAX and that particular label is kind of related? Okay. So the instruction to make that pointer a null pointer is moving a 0 into struct1 underscore PTR, which is a displacement from the member PTR from the beginning of a struct1, but who points to the base of that structure? EAX. So I just use EAX as my base register, and that's it. So when you look at the assembly language implementation, let me turn on the line number here. So when you look at this, line 10 and line 11 of the assembly version is implementing this code written in C. Yay, we are all done, and we got 10 minutes left. What else am I going to do in this class?
What's the hard way?
Well, not exactly the hard way, but I'm going to throw a wrench into this whole thing and say, but what if I change the structure definition? Okay, so hypothetically, if I go to the structure definition, okay, so let me switch back to this window here, and I go to struct1.h and say, oops, and I say, well, you know what? I forgot about certain things, okay? I forgot that I need another variable here, another member here, another member J, and, you know, okay, that's it. Now I have to go back to the assembly file and change the displacement to member PTR in the struct1. So every time I make one change to struct1, I have to go back to the assembly language file and make adjustments to the displacements, which is really, really cumbersome. I don't want to do that. Do you? Okay, so I want this program to automatically update something when it redo everything so that I don't have to worry about this at all. Okay, in other words, I want this program, or I want this project to respond to changes to struct.h so that every time I update the definition of the C structure, it will do something so that the assembly version of the same subroutine that depends on offset to individual members will get updated automatically, so I don't have to worry about a single thing. Okay, so the first question is that even possible? Yes. Well, it is possible, but there are a few things that we have to do to set up first. Okay, so the first thing we have to set up is, okay, I'm going to get out of the editor for now. Okay, so the first thing I'm going to do is to change the program called teststruct1.c to basically, I'll call this, struct1 include file generator.c. Okay, and I'll just change it a little bit. And from the way I change it, I think someone in this class will figure out how I'm going to proceed with this particular scheme. I'm going to take that away. That's not needed. So instead of printing something that is meaningful to us, I'm going to print something that is meaningful to the assembler. Okay, so I'm going to say struct1 underscore I equals a particular value. Same thing that we have defined before. Same thing here. Struct uppercase struct1 underscore a equals another number. Same thing as we have defined before. And then this one, the same thing. Struct underscore ptr equals to that. Okay?
You add one for J?
I can add one to J, but since the assembly program is not referring to J, it doesn't really matter. But since I do have J here, might as well. So we'll go ahead and add another entry for J. And of course, at this time, I really should define a macro to do this. Macro in C. There is a way to use a macro to do all of this stuff here. Does anyone know how to use macros in C and C++? No? Okay, so I'm not going to talk about that. We'll just keep this program the way it is, okay? Because I don't want to add another layer of language on top of what we are talking already. Okay, so this is good. This is fine. Okay, everybody can understand this part. Okay, so I'm going to just test this program to make sure that it works. So struct1 include file generator, and then we give it the source file like that. Compiles. Let's run it. Okay, it runs. It prints out the displacements to individual members of the structure. And does it look like something that the assembler can take in to define labels inside the assembler? Yeah. So I can redirect this to a file, right? So I can run this program again, and I just redirect it to struct1 .inc, not .h. I have to change the extension to distinguish the include file in assembly as opposed to the header file in C. Not a problem. Take a look at struct1.inc. It has the content that we think it should have. No problem so far. Are we still doing okay so far with this experiment? So now we go into more useless .s, which is the assembly file, and then we say, well, I guess we don't need this anymore. Instead, I'm going to do a pound include struct1 struct1.inc, the file that I generated from the C program. Okay, so we have a few steps here. We have the .h file, the header file intended for the C program. We have struct1 include file generator as a C program to generate the include file. Once the include file is generated, I do a pound include inside my assembly language program to include that so I can define the displacement of individual members from the beginning of a struct1 object. Okay, so now I can see if this will assemble. Okay, so we'll do a gcc-c, because I just need the object file, I don't need the executable. More useless.s, and it works okay. Great. But at this point, every time I change the header file, struct1.h, I have to go through all these steps manually, which is cumbersome. So I want to fix this, so that I don't have to do this all manually. I want to do this all automatically. Which tool do you think is suitable for this task? Make. Okay, the make utility program. Okay, so what we will do is we'll copy one of the files that we have done already. So I have to pick one that is recently done, that has the header file or make file. So I cannot remember any one of these has a make file. Let's find it. Nope, nothing. Well, we have a few down here. We have under downloads. Okay, so I'm going to copy. Link has it. Local var has it. Okay, so we can just do one of those. Is this where the program is located? Yep, it is. Okay, and that's okay. I can just copy that. So I'm going to copy downloads / link make file to over here, and then I need to make some changes to make file, because in this case I need to do a few things. I need to define another executable, which is the include file generator executable, and I'll just call it the same way that I used, which is struct1 include file generator, and then I have include generator source file. That's struct1 inc gen.c as the .c file. The assembly file is not linked anymore. It is called more useless.s. The executable is main. Well, let's change that to test struct1. And I think that's it.
Header.
Sorry?
Header. Header. We have header file.
The header file. Well, the header file is going to be taken care of automatically. Okay, so before we do any of this, okay, let's just test whether the automatic include is going to work or not. Okay, so I'm going to undo all of the things that I did earlier. Okay, so undo everything, and all I really want to do is to generate the include file. That's all I want to do at this point. So the C file that I want to compile is struct1 include file generator. That's all I want to do. And the executable will be named accordingly, struct1 include file generator, like that. And there are no assembly version code that I want to deal with. This is all that I want to do. Make clean. Make clean. So I'm going to remove all the files for this particular project to make sure it's clean. And then I just say make to create the executable. So what I want to test is if I change the header file, will the make utility program know that it has to recompile the .c file? That's the first thing I want to test, because if that fails, I can forget about the rest of what I want to do. Okay. So to change that, I just need to change the timestamp of the header file. So I'm going to change the timestamp of the header file just by touching it. It's not going to change the content, but it will update the timestamp on that file. And then I run make again. It is going to recompile the files automatically. Yep.
You need to redirect now.
Say again?
You need to redirect now.
Yeah, I need to do that next. But I just want to make sure that the automatic recompiling part is working, at least for the C program. So why is this so automagical? What makes this so automatic?
It's programmable.
There is a file that is doing all this trick here. The dependency of the executable on the .h file, the header file, has to be captured somewhere. It has to be stored somewhere, represented somewhere. So where is it actually represented? It is in the .d file. Okay, so if you look at struct include gen .d, struct1, that is the content of that file. Does this look like a rule that the makefile would take? It has the target, a colon, and then a dependency list. Okay, what file do I need in order to create the target? So it seems to automatically understand that the .c file is needed and a .h file is needed as well. But when did I create this file, the .d file?
During the makefile.
The makefile. I did not create this file. It is created automatically. So what I can do again is to make clean. Okay, so now it's all clean, and you can see that the remove instruction is going to remove the .d file as well. So when I do make again, you can see how it is generated. The first command is the one that generated the .d file to begin with. In other words, every time I change the .c file, it is going to trigger that rule to regenerate the dependency file. When it regenerates the dependency file, it will go through the clean processor. It will analyze the entire hierarchy of all the pound includes to make sure that the .d file reflects the dependency correctly. So this is why it is called, so automatic. Okay. So after this, I can now start to do something else. I can go back to the makefile, and this time I also want the include file to be automatic, the .inc file to be automatic. So I can now indicate this is my include file. It is called struct1.inc. And that dependency cannot be automatic. I do have to specify that one here. So I have to say, inc depends on the exe file. And the way I use the exe file to generate the include file is to run the exe file and then redirect the output to the target. And the target has a particular internal symbol or internal variable called a $@ that is basically a short form of the target. Okay, the file that depends on the executable. Okay. So if I do a make struct1 include .inc, gen not found. And then it says it's up to date. It did succeed. Oh, okay. I see what's happening because I forgot the /. I think. There we go. So now this part is automatic. I just want to push it one more step, and then that will be the end of today's class, okay? Because I just want to show you how the make utility program is really, really useful for all kinds of different project files, okay? So what I want to do is I want to go to the make file, and this time I do want to specify the assembly file, and it is called more useless. More useless .uppercase S. And then we go to more useless .uppercase S and make sure there's an include here. Okay. So I say make clean up everything, and make sure that I also remove all the include files like that, and I do a make. Oh, it doesn't work. Okay, fatal error, no such file or directory in.
Trying to do the count include on a file that doesn't exist?
Right, but it's not resolving the dependency correctly, because if I do this manually, it will still work. In other words, if I do this part first, it's still not working.
I think you deleted it.
Sorry?
I think you might have deleted it. That the asterisk.
Yeah, you deleted all your include files.
Right, but it should automatically recreate the include files. All right. I'll give it 5 minutes. If I cannot fix it in 5 minutes, we'll do it next time. Okay, the source file is a.src, and there's this to include that. Okay, so it did not generate any of those files. Okay, this might work. It's a chicken and egg problem. Okay, it is working now, except it is still empty. Circular dependency dropped. Okay, so we have a circular dependency. I have to think about how to resolve it. It'll be done next time. But when it's done, it's really cool because I can make one change to the header file and it will update everything that is needed for the assembly code to work.
I have a question about my virtual machine. I have problem with time synchronization.
Okay.
So make program doesn't work.
You can do a touch asterisk to touch all the files so they all have the same timestamp. So you can do this.
And my time in virtual machine is like behind. I don't know why. I need to update it like every day.
Okay, so do this in your virtual machine and see what is the date code.
It's behind.
Is it using UTC or?
Probably.
I know why. It has to do with the VirtualBox.
I put mark that synchronize time. It doesn't synchronize at the moment.
Oh shit, that's a pain. So you
You
rear
use
end
Windows,
something
right?
else?
Yeah.
Okay, in Windows, the real-time clock is storing
Oh, then it's your
local
fault.
time instead of the UTC stop. In Linux, it's assumed to store
Oh,
the
that was your
UTC
back,
time.
not your front?
So what you can do is when you started the virtual machine,
That sucks. Well, at least you
you
get
can
paid
go
for it.
to System.
You get paid for it.
There should be a way to change the real-time clock, how it appears to the virtual machine.
If I touch file, does it assign like past? Or could it update time like for past time? Or not? Or only for future time?
You can reset it to past time too. One thing you can also do is to install a particular package. So you can go to aptitude as root.
Yeah, I read about time protocols.
Yeah, UTC, UTP, sorry, UTP.
Yeah, UTP.
So you can install the UTP program
Can I have my test?
Yeah, you can.
So my question just was if it shouldn't be automatical. I need to install UTP or something.
Yeah, you have to install UTP, the time server.
Yeah, I read the internet, but I just decided to update time is faster.
So, do you understand the last bit of it? So you're using a program to print out into a file, and that file gets pasted on top of the assembly language file.
Well, I'm using a C program to generate an include file, and the include file is in return used by the assembly file.
and you just paste it in there.
Right. Yeah. But the make utility program is not resolving the dependency correctly, and that's why it's having problems.
Next lecture.
So that's what I need to resolve. Is why is it why is it a circular reference? No. I probably have the answer. I just have to find it myself.
I have a question about homework.
Yep.
For the factorial, is there like max?
Well, since we're using 32-bit integers, we can only go up to a certain number. Is it 12? Okay, so there you go.
If they went over 12, then it would put something to EDX or something. I have no idea.
Well, EDX stores the most significant 32-bit of the product of the multiplication. So when the multiplication exceeds what you can represent using 32-bit, the EDX starts to become non-zero. But we are not going to use it because the return value is only paying attention to EAX. And that's why that part is never really used. And
So as long as you can get the 32-bit, like anything that can fit inside there.
right. So you can only work with numbers where the factorial can be represented by 32.
I have a same question. So if it does 0 to 12, that's okay?
Yep, exactly.
We don't have to do validation of any kind.
Do you have any idea what I did wrong?
Cannot connect to clam B. It has to do with the internet access. Can you ping Google?
Oh, it's a screenshot.
Sorry.
Here's the.
I thought
Here's the
actual.
Yeah. The
Okay.
virtual box.
Okay. So you cannot ping Google. That means you don't have internet access right now.
Do I have to go to close it and to make it host only?
If you make it host only, you will lose internet access.
Okay.
So when you're still installing stuff, you have to use the other one. So that's why when you do the CLAM FS homework assignment,
Yeah.
You have to enable internet access. So switch it back to NAT.
Okay.
For this assignment, when you do the other homework assignment,
Yeah.
then you can switch to host only.
Okay. Because this one does have access in it, and I can update packages.
You can?
Yeah. Watch. See, sudo apt-get update. Sorry. Aptitude update.
Okay.
See?
Let me